Okay, I guess we can get started. So last time we introduced the definition of Lamplighter groups. And basically one reason why we talk about Lamplighter groups first is because they're already an interesting example of somewhat intermediate behavior where the Poisson boundary could be trivial or non-trivial according to various parameters. So it's kind of an interesting example. So the definition that I already gave is if the dimension, then we define the Lamplighter group is okay GD. So it's the semi-direct product of ZD and a abelian group. So depending on how you write it, so let's say that you put well, anyway, yeah, let's say you put ZD first, then you put the product of countably many copies of Z2, so they are indexed by ZD. And so what is the action? Well, there is an action of ZD onto the other group. So there is an homomorphism from ZD to the automorphism group of this infinite countably generated abelian group. And so this one is the normal subgroup. So this one is a normal subgroup, so you need to write like that. Okay, so okay, and the action, where the action is given by well, basically you take X, which is a point in the grid, and it has to act on an element in this infinite abelian group. So remember that this infinite abelian group represents the states of all possible lights. So the idea is we have a grid, and at each site on this lattice you have one lamp, so it's either plus 1 or 0, let's say. And so you have an element called Z mod 2Z at each site. And so the space of all possible lights is a copy of this, especially if we assume that at most finitely many lights are on at every step. So this means that you can take the sum rather than the product. And so the action is given by translating the configuration. So F is, you can think of a configuration, right? So configurations of lights, well, is a function from ZD to Z mod 2Z gives you at each step, at each site, the state of the light. So in that sense, you can say that this F is an element of this product. Supposing that if the support of F is finite. Okay, so the action here is just that for every other point Z in the grid, the action is F of Z minus X. Okay, so this gives indeed the intuition that you start at the origin and all the lights are off, and then at each step you can either walk one step along the grid, or you can switch the state of the light, so from on to off to on. So that's the definition of the Lamplighter group. And so we saw already the following facts, we saw that GD is finitely generated for every D. So again, this is exactly the reasoning that the generating sets are the generators for the underlying abelian group, so for ZD. And one element which corresponds to switching off or on the light at 0, because you can see that by composing those, you can go anywhere and switch on and off the light there. And so the other one is that GD has exponential growth. Again, for any D. And what is the intuition here? Well, the intuition is that if you fix a ball in this lattice of radius r, the space of all possible configurations that you can have with supporting that ball is exponential in r's, like 2 to the, it's 2 to the cardinality of the ball. And so, and on the other hand, if you do basically in 2R steps, you can turn on or off any lights that you want, because you can walk there. It takes at most R steps to walk there, and then you can change the lights. So you can see that this group has exponential growth. Okay, so now the more subtle thing is, what is the Poisson boundary? By the way, what is the actual growth function? This is a much harder question. So we just showed that the cardinality of the elements G, such that the norm of G in the, say this generating set that we constructed before, is bigger than n, where we saw that this is bigger than 2 to the n over 2. But what is really this function? That's a much more complicated question. Oh yeah. Okay, so now let's look at the Poisson boundary. So here's the theorem. If you do the Kamenovich and Vershik, is that if you let mu be a finitely supported symmetric, symmetric is important here, generating measure on GD, then the Poisson boundary of GD mu is trivial. Well, if and only if D is 1 or 2. So recall, generating means means that the semigroup generated by the support of mu as a subgroup is the whole group. So this of course respects the recurrence and transit property of the van der Waals. So there is obviously relation with that. Okay, and so let's see some proof. There will be again two proofs. So the first proof would be an entropy calculation, because we did this entropy theory. So we want to apply it to see whether it has a bearing on the random walk and on the boundary. So the first proof would be entropy calculation. Okay. Okay, so recall, of course, that we know that the boundary is trivial if and only if the asymptotic entropy is 0. So recall the entropy criterion that the Poisson boundary is trivial if and only if the asymptotic entropy is 0. Because this measure is finitely supported, so for sure it has finite entropy. So we have to maybe compute the entropy. So let's see. So what we need is a probabilistic statement lemma, you might have seen before, which is Kolmogorov's inequality. So some sort of large deviation statement, which is the following. So we start with xn, a sequence of IID. Random variables. I don't even know if we need the variables. And suppose that the expectation of xn is 0 and the variance is finite. And let yn to be just the sum of them. Then the probability that the max of yk is bigger than certain lambda, it's bounded above by the variance of yn divided by lambda square, or lambda. Okay, so this is a classical the large deviation estimate. So why do we care about this? Because the idea is that we have our lamplighter. So let's look at the computation in one dimension. So we have a lamplighter. And what do we want? Well, the idea is that most of the time, of course, the random walk on the lattice on ZD will be at distance roughly square root of n from the origin. So the distance between the n step, let's call it xn, the n step, will be roughly square root of n. And we can use that to compute the entropy. So basically, the idea is that most of the time, the walk will be within the square root of n radius, and then you can do a sort of counting. And then there is another case, which is where the distance is large. And if the distance is large, then, well, that's a sort of a small probability event. So we apply another type of bound. And this makes it precise what is the deviation. So the trick here is to set lambda to be something slightly larger than square root of n. For instance, n to the 3/4. That would do it for dimension 1. So for dimension 1, right? So we set lambda equals n to the 3/4. So most of the time, clearly, the probability that the max is bigger than n to the 3/4 is pretty small. That's the idea. And so, okay, and how do you apply it? Well, okay, we call, so Wn is a random walk on the Lamplighter group. It has two coordinates, xn and fn, right? So xn is in zd here, z, and fn is in place of configurations. And of course, so the idea is that the random walk projects to a random walk. So the random walk in GD projects to a random walk on Z just by looking at xn fn goes to xn. So since mu is symmetric, so is P star mu, which is a measure on that. Yes?
I'm working on a projection because if you're changing the path, that would be making zero progress instead.
You're changing the f, you're making zero progress. Yes.
Maybe I missed it.
And so what?
It's not working.
No, you can stay still. It's fine.
Oh, okay.
It's still a random walk. There's a probability that you don't move at each step.
Oh, okay. Yes. All right. Yeah.
It's still a measure on. Yeah, what you have to check is that this is a homomorphism.
Identity has non-zero measure.
Sorry?
Just like staying still, it has non-zero measure.
Yeah, exactly. It's a random walk where staying still has non-zero measure, but that's not the problem.
Yeah.
Yeah. Okay. So yeah, so there is this walk on Z, and then we clearly just apply we clearly just apply this clearly because that since P mu is symmetric, well, this corresponds to the increment we have average of 0 on the projection. Maybe if we want to stay more in touch with that notation, we could call this yn instead of xn, just for right. So in this walk, you have yn equals x1 plus xm. So these are the projection of the increments. So this one is a random walk on Z. And the expectation of x1 is 0. Yeah, since mu is symmetric. Since P star mu is symmetric. Okay, and so we know what is the probability of having a sort of large event. So the probability that the max of the yn of the yk is bigger than n over 3/4. Well, this is less than the variance of yn divided by n to the 3/2. And then obviously the variance of yn is the sum of the variances. Again, this is just random walk on Z. So this is n times the variance at one step. So this is n times the variance of x1 divided by n to the 3/2, which is some constant d, which is this, divided by n to the 1/2. So the good thing is if we pick any power which is bigger than 1/2, this goes down, and not just goes down, but we have control on how fast it goes down, and in fact it's polynomial. Okay. And so now we define the set an, which is the set of yf such that norm of y is at most n to the 3/4, and the support of f is contained in this interval from minus n to the 3/4 to n to the 3/4. So this is the large set. This is the likely event. And then the complement will be the unlikely event, and then we have to do the estimate. Now it's kind of, it's not that's strange how to do the estimate here. Let's see what's the classical way to do this. So okay, so first of all, the cardinality of an. So how big is the cardinality of an? Well, right. So we have that for f, we have two choices for each site. There's two n to the 3/4 sites. So it's 2 to the 2n to the 3/4, I think. And then we have the cardinality of the possible projections is again 2 to the n to the 3/4, I think. So what is kind of neat of this is that this is still sub-exponential. Because this n is to the 3/4. So right, so if you do 1 over n log cardinality of an, well, this is 1 over n, right? So this is 3/4 log n, which is kind of small, plus, okay, plus log 2, okay, matter, plus this guy. So 2n to the 3/4 log 2. Right? So what it matters is that this is upper bounded by, right? So this is n and n to the 3/4. So basically it's n to the 1/4 in the denominator. So it's upper bounded by some constant to the n to the, you see, 1/4 minus epsilon. Yeah. Because, okay, there's the log, okay, but the log is, sorry. Yeah. Anyways, this is maybe you don't even need the epsilon, right? Because no, right? You don't. Yeah, you don't need the epsilon. Okay, very good. So that's even better. Okay, so that's nice. And then the other thing is the complement. And so that what's the issue with the complement? The complement is it has small probability. Right? So probability of an complement so we know that, yeah, we know that this, right? So the n complement means that the walk has gone up above, out of this bounded box. So the probability of the complement, yeah, in a sense that Wn, yeah, the Wn is in a complement is bounded above by d over square root of n. Okay, and now we can just do the estimate of the entropy of the nth convolution. So we know that this is, by definition, is the sum of mu star ng log mu star ng. And classically, we can split this into two terms. One is in A, and the other one is in A complement. So it's G in A n, And G is an AN complement. Okay, and then we kind of do the Jensen's inequality. Like you want to say that we want to estimate the entropy with the cardinality of the set, more or less. But yeah, but you need to have a probability measure to do that. So you have to normalize slightly. Okay, so this is what? This is mu n of AN times this guy. So sum over G in AN. This is mu star n G divided by mu star n AN. So we just do that. And this is log of 1 over mu star n G, like that. And then minus this other thing. Okay, and so what? So then, well, again, this is a measure on the set AN. So you're taking the average of this function. And so we can apply the Jensen's inequality. So there is mu star NA here times the log of the sum. Right. So we put instead of, so this is the weighted average of log of this. So this is less than log, bringing this inside. Okay, and then the second part. What is the second part? Well, the second part is, you see, this is oh yeah, so what we can say is we can set, we should maybe set it somewhere where we can set the delta to be the minimum of mu G, where G is in the support. So this is a finitely supported measure. So in that case, you know that the minimum of mu n G is delta n. So the mu star n G is bounded above the down below by delta to the n if G is in the support of mu n. Right? That's just that's just because you can do n steps. Each step, the probability of each step is at least delta. So if you n steps, you do delta to the n. Okay, and so this is used to estimate this one, because log of mu n G, right? So minus log of mu star n G is bounded above by delta by n log 1 over delta. It's just this is a pretty standard thing. So okay. So if we add that, well, we have mu star n of a complement. If you're summing over this, and each term is log of that. So times n log 1 over delta. Okay. So here we have nearly simplification. And then you finally have this famous cardinality of an here. So you get less or equal than mu star n an log of the cardinality of an minus mu star n an log mu star n an. This is from here, because you get log of this gets the minus here, and here you have the cardinality of an. So you get that, and then you have this one. And then we know this one, how big it is. So we know that this one is bounded by 1 over square root of n. Right. So this is plus what? Plus d, this d log 1 over delta that we discussed before. And then we have n divided by square root of n. So we are in good shape because, right, so clearly, okay, this one is uniformly bounded. So this is just x log x. So it's some constant. So this is less than 1. So this is bounded by log of the cardinality of an plus some constant that we don't care about, plus d log 1 over delta square root of n. But clearly, this is sublinear in n. If you take this divided by n, clearly it goes to 0. Right, so this is small o of n. So h of mu star n divided by n goes to 0. So yeah, so this is a classical technique of how to estimate the entropy. Usually there is a likely event which has large probability. And if you know that the walk is somehow constrained somewhere with high probability, you do this type of estimate, and then there is a remainder term that you deal with in the other way. Okay, so you can do a similar computation for d equals 2, but yeah, so it's a good exercise to think about. It works for d equals 2. It's not so complicated once you think about how you have to do the, yeah, you choose this threshold and you count. But obviously it doesn't work for d equals 3 because otherwise the proof would give triviality of the boundary for every d which is not true. Yes.
What lambda should we pick?
Yeah, it's a good question. That's what the exercise is about. Yes. Yeah. So yeah, that's a slightly, yeah. Okay. So this is a explicit way of doing it. So there's also another way of doing it, which is more soft in a way. So the second type of proof, the second proof is about recurrence. Right? So the second is about the recurrence. So the recurrence is given by the fact that, again, as you know, the simple random walk or any symmetric finitely supported random walk on Z1 and Z2 is recurrent. And so if we can use that to our advantage to prove the triviality of the Poisson boundary. And the answer is yes. So the definition is like this. So let H inside group G be a recurrent set. What does it mean? i.e., for any H in H, the probability that Wn being in H for some n bigger than 1, given that W0 equals H, it's 1. Right? So we have a group G, and we have a set. In general, usually it's a subgroup, but it doesn't have to be. So suppose H is a subgroup, and then we call it recurrence if start from H and there is a positive probability 1 of coming back to H. Right? So in that case, we can define an induced measure on H by taking the first return to H. Then we define the first return measure. Mu induced on H, as you would expect. So mu induced of G is the probability that there exists an n such that Wn equals G, and the G is in H, and Wn is never in H before, and Wk is not in H for k less than n. Okay. So you do a first return. So you start, let's say you start at the origin. Let's say that the origin is contained in H. I mean, it will be a group for all purposes. So we just do that. So now we start at E and we say, okay, we return in H. So now where do we return? Well, suppose we return at some G here. Well, we assign to G the probability of exactly this event, the probability that the first return hits exactly a G. So that's clearly a probability measure because the set is recurrent. And if that's the case, so the lemma to Furstenberg is the following: is suppose H is a recurrent subgroup. H is a recurrent subgroup of G. Then the Poisson boundary is the same. So then the Poisson boundary, the Poisson Furstenberg boundary of G mu is the same as the Poisson Furstenberg boundary of H with the induced measure. So you can think of it like that you have this, the way you construct this Poisson transform, or the inverse Poisson transform, is taking a limit, right, of this function using using this martingale that you get by running this walk. And so basically, you can take a limits just on a subset of the possible times by just by looking at the times where you return to H, because you're gonna return to H infinitely often, almost surely. And so basically, it's like, say, if you have a harmonic function on H, you can extend it to a harmonic function in G by you know, by running the walk, at some point you hit some point in G, but then the same path will also return to H infinitely often. So that's the kind of idea in this lemma. Okay, so we did, yeah, we will not prove this lemma in detail, but that's the idea. So but once you have that, then you can see that if the projection of the random walk is recurrent, then the walk is trivial. So recall the second proof. So the proof that for D equals 1 or 2, the Poisson boundary of Lamplighter is trivial. Again, if we have this finally supported and symmetric measure, well, clearly you consider the short exact sequence like that. So we have that. You see, you can every path and the Lamplighter you can project it to ZD, and the kernel is this infinite abelian group, right? And so you call GK the kernel. So yeah. So call GD0 the y f such that y equals 0. So this is the kernel. So space of configurations where the walker is 0. And so you want to say that this is a recurrent subgroup. And it is a recurrent subgroup because the induced random walk on ZD is recurrent. So almost surely you're gonna come back to GD0 infinitely often. So since the random walk on ZD is recurrent, GD0 is also recurrent as a subgroup. Okay. So now clearly you see where this is going, because so the Poisson boundary of GD, this measure is isomorphic to the Poisson boundary of this induced walk on GD0. And what is kind of cool is, okay, so this induced measure does not have good moment conditions because you don't know anything. I mean, this you can return very far from the origin. So this measure is certainly not finally supported. And really, we don't know too much about even the moment conditions. But it doesn't matter because this group is abelian. So since GD0 is abelian, and okay, the only thing you want is mu n is symmetric, which it is because everything is symmetric. So even the induced. So then the Poisson boundary of this, since this is an abelian group, it's always 3. Yes? Sorry? No. No. It's the it's the walker is at the origin. The configuration could be anything. Right? You start your grid. You start. You do a bunch of stuff. You can turn off on some lights. Then you come back to the origin. But the state of the lights could be anything. Yeah, it's not just this is a setup of states where the walker is at the origin, but the state of lights could be anything. Yeah. So it's like it's a big group, and in fact it's isomorphic to this one. Yeah. So then clearly this one is trivial, and so also Poisson-Furstenberg boundary of the whole group is trivial.
Why is it being ability to apply the boundary trivial?
Oh yeah, so I think we actually proved it. Yeah, so for any measure on an abelian group, it doesn't matter whether it's finally supported of anything. So actually, I think the proof that we saw, in fact, proves it in general. So yeah, you don't need the finite support for that. So yeah, because you look at the harmonic functions, look at the minimal harmonic functions, you translate harmonic function, you get another harmonic function. This is where the abelian property is used. So yeah, so this induced measure is kind of not so nicely behaved, not in general, but it doesn't matter because because as long as the group is abelian. So this is very nice. Now you can see this argument adapting, because anytime you have a semi-direct product like this, and you have projection onto a recurrent random walk, you can do this argument. Now this argument also gives you the opposite in a way, because it tells you that if the random walk is instead transient, then the Poisson boundary is non-trivial. So why is that? Well, so let's write this down. So far we proved the triviality part. Now let's look at the non-triviality part. Non-triviality is easier, but then the identification is the hard part, in fact. So in fact, so the theorem, or maybe lemma, because the big theorem we wrote before, the following, that if given GD, if the induced random walk on ZD is transient, then the Poisson boundary is non-trivial. This particular measure is non-trivial. And what's the proof of this? Well, it's kind of the opposite. So what does it mean that one dimension? What does it mean that the walk is transient? It means that, you see, there is a positive probability that you're escaping from zero, right? So there's two things you can say. So since the random walk is transient, okay, we need a high dimension maybe grid to make it more believable. So what you want is, you see, it's transient. So after final, eventually, almost surely, eventually it's gonna exit any compact set. So almost surely the support of the lights will be stabilized. So for any compact set, compact K inside ZD, yes, almost surely the walk almost surely never return to K. And so at some point, right after some number of steps. And so the support in the lights is will stabilize. So the support of F and intercept K eventually stabilizes. And so we can define F infinity of your path omega as the limit. And n gets infinity of Fn of omega. And where does this live? Well, this lives in the product, not in the sum anymore, but it lives in the product of all this finite groups, because you see that the configuration of lights need not be finitely supported in the limit. At each step, it's finitely supported, but you can take a limit, and in the limit, it need not be finitely supported. You could turn on all the lights on this geodesic, for instance. But there is a limit, because you cannot change. Eventually, you cannot change your path because you're going to infinity. Okay, so this is a natural function that you can define in the transient case. And so, in fact, there is a function right from omega p. Yeah, there is this function F infinity to this infinite product. And so there is a new measure, it's infinity star. There's a distribution of this. So, and this is clearly a boundary. This is clearly boundary behavior. So it's a function that is invariant under time shift, because it's obtained by taking a limit. Right. So the event A, which is all the omegas in omega, such that F infinity of omega is whatever, for instance, is 0. Yeah, whatever given configuration of light you prefer. For instance, they're all off. Okay, so we can consider this event, and this is a tail event. Meaning that T inverse of A equals A. And so if we know that there is one tail event which has probability neither 0 nor 1, we know that the boundary is non-trivial, because that's another way of thinking about it. We said this before, that boundary trivial means that the only tail events have probability 0 or 1. But this event has neither. Right. Why? Well, why? Let P1 be the probability that the walk returns to 0. After one step, so okay, sorry, the first time, the probability that the walk returns to 0, well, this p, you see, this p is neither 1 nor 0. Because if the walk returns to 0 with probability 1, then the walk is recurrent otherwise. So it has to be something like that. Okay, and so what? So now what is the probability of this set A and the probability of the set A complement? Right. Oh, sorry, the probability walk never returns. Sorry. No, it would be the same, but let's say the opposite, the probability that never returns to 0. So, okay, so the probability of A is bigger than P1. Because what you could do nothing and then never return to 0. And then your limiting configuration contains 0. Yeah, I guess what you want to say is, sorry, the following. When you say that the limiting configuration at 0 is 0. Yeah, so you want to say that in the limiting configuration, the light at 0 is off. Okay. So clearly what you can do is, again, you can do nothing and never return to 0. And so the limiting configuration would have the light at 0 being off. The other one is, well, you can switch the light. Yeah, so if the probability of switch light at time 0, at 0, and then again never return to 0. So it's also another thing you can do. So that's another. So both of them have positive probability, and so they're complementary events. So clearly we know that the probability of A is neither 0 nor 1. And so the Poisson boundary is non-trivial. So let's recap. So we have this transient random walk. So since it's transient, almost every light configuration stabilizer. So you have an infinite limit to the arrangement of lights that you've seen. And then you're just looking at the question whether at infinity is the light at 0 on or off. And so both of them, both this event and the complement have positive probability. Because what you could do is do nothing now and escape to infinity. This is some positive probability. Or now you switch on the light and then you escape to infinity. So both of these events have some positive probability. And so the actual probability has to be something intermediate. So that's it. Okay, so now we're done with this part of the lecture. Let me just say one more remark. So some sort of historical remark is that so far we proved that, you see, this boundary is non-trivial, but of course we have an obvious candidate for the boundary. So we have this F infinity map. So obvious candidate would be that the space of infinite configuration of lights with this induced measure would be the actual boundary. Right? And this is in fact being proven, but it's much harder to prove. So in fact, for D bigger than 3, the Poisson boundary, of this lamplighter with this measure mu is isomorphic to this infinite space of configurations. But this is a later theorem. So in fact, for D at least 5, this is due to Eschler. Forgot in which year, around 2010 or something. And then for D equals 3 or 4 is even more recent by Harris and Lyons. And this is like maybe 2016, 17. So in fact, it is true, but it's more complicated. So far we have this A mu boundary, which is non-trivial. So the whole boundary has to be non-trivial, but we don't know yet that this is maximum. Okay, very good. So I think we can take a well-deserved break. So maybe another 10-minute break. Okay, so I guess we can restart. Okay, so we discussed the more or less at least the basics of the theory for lamplighter groups. Now, what we really care about for the end of the course is to identify Poisson boundaries for other types of groups, so groups that have some hyperbolic properties. So they act on some space that has some maybe weak hyperbolicity, but still something like that. So in order to do that, so those groups have non-trivial boundary most of the time. So what the problem is not to just prove whether the boundary is trivial or not, but really to figure out what is the model for the Poisson boundary. So in general, to do that, we need the conditional entropy theory rather than the just sort of absolute, so to speak, entropy theory. So there's another type of criteria which is similar but not the same. So recall, so in the geometric situation, we have again G mu a measure group. And G acts by isometries on a metric space, on a geodesic, let's say, metric space. Maybe geodesic is not always needed, but that. And then again, X has bordification. X equals, sorry, X bar, X in bar. And suppose we know for a base point O in X, we know that the limit of the sample path WO exists on the boundary. Okay. Again, this is the picture. And then mu is the hidden measure. And so in that case, we know that in that case, so we know that the boundary of X with mu is a mu boundary. Well, this is already proved. And so the final goal is to prove that the boundary of X with this hidden measure is not just a mu boundary, but is the maximal mu boundary. B. Hence, it is the Poisson boundary. Okay. So that's the general goal. And in order to do that, we need a conditional entropy to determine that. Okay, so again, we assume that the entropy of the measure is finite. This is a very strong assumption. Well, it's assumption that is needed for talking about this entropy. So somehow we're always in this realm. Okay. So first of all, what can we say? Well, first of all, we can define a conditional measure. So recall that you have omega p is our space of infinite paths, and there is a map. Let's call it BND boundary map to some B nu. So this is a mu boundary. So whenever you have a mu boundary, for instance, in this case, or in general, you have a boundary map from the space of infinite paths to this space. So if we pick a point in this boundary, we can disintegrate the measure. So we can disintegrate so the measure P, every time you have a measurable map, again, here you're using this fact that this is on a backspace, so it's a nice measure space. You can do the integral. This measure is the integral of conditional measures. Let's call them P psi, B nu psi, over B, where P psi is supported on the preimage on boundary inverse of psi. So every time you have a map, measurable map, the measure theory tells us that you have B here, you have omega, and you have a sort of vibration in the sense of measure theory. So you have a measure in the global space, and on each fiber, or at least on generic fibers, there is a measure which is induced from this, right? So that's the classical disintegration theorem. And now there is also a process associated to it. Right. So in fact, maybe we can even leave this picture here. So if we do it for I run a walk, right? So we are fixing a boundary point, and we're looking at all the paths that are converging to here. Those could be many. But however, slightly unfortunately, the set of such paths has measure 0, obviously, because typically the boundary is uncountable. So that's why you need this disintegration theorem. So each fiber has generically measure 0. And so, yeah, this is a bit of an issue, of course, whenever you have conditional probability. Okay. But we can define the conditional entropy with respect to B nu is what? Well, H of P psi well, there's various ways to define it. One is the limit as n goes to infinity of the entropy of the n-step distribution of this conditional walk. So where you see mu n psi of g is the probability, right? This p psi that Wn equals g. So at least this tells you that it's defined, right? Because there is the space of paths that converge to psi has some measure, some probability measure. And so there is a certain probability that the n step equals g, conditioned on the fact that you're hitting psi at infinity. Okay, this is not super reassuring because it's still very abstract. This integration is still very abstract. So, in fact, it turns out that there are easier, I mean, not super easy, but there are ways to think about this as a discrete process. But let me first write another thing. So we can write the entropy criterion. Entropy criterion for the not the relative, the absolute case, but the relative case. Yeah, so this entropy criterion is definitely due to Kaymanovich. I think he was the one who pushed it from the absolute to the relative case. And it's the following. It says that, yeah, so if H mu is finite, and again, B mu is a new boundary, is a mu boundary, then B nu is the Poisson boundary. Well, if and only if this relative entropy, HP psi, is 0 for nu almost every psi on the boundary, on thing B. So again, what is the idea? So maybe we can also maybe next time prove it, but what is the idea? The idea is that, you see, this boundary that you're given, is it the maximal possible boundary? So can you further split this boundary points in some other, finer partition? And the answer is, well, if the relative or conditional entropy is 0, means there's no more information, right? So it means that, once you know the hitting point, once you condition on that, then there's no more information encoded in this. So the relative entropy being 0 tells you that there's no further splitting you can do because there's nothing else. So the information left over is 0. So there's nothing else that you can construct from the point of view of measure theory, right? I mean, you can, as a set, of course, you can always split. As a set, you can always split points to other sets, but from a point of view of measure theory, all the boundaries, any boundary that refines this one, will have to be isomorphic to this one as a measurable G set. So that's the idea. So how do we use this? Well, that's the interesting thing. So how do we use this condition? So the easiest way to use this is to know something about the action of the group on the inside. And so this is related to so this is always true, but the question is now, if you're given a concrete situation, how do you use it? So the first way to use it is called the ray approximation criterion. Which is related to so-called the sublinear cracking property. So what is this? So basically, we look at the following. Let G mu be again a group of isometries of a geodesic metric space XD. Okay. Okay, and let mu have finite first moment, for instance. So what does it mean? Let's recall that is the integral of distance between O and GO. That means G finite. And let L to be the drift of the walk. So the limit. So we know that under this condition, the drift exists almost surely. Could be zero, but in general, it could exist. Okay. So now what do we want? So we are in this situation. So suppose we are in the situation where the walk converges to psi. But now the question is, how well can you approximate? Suppose, so I know that the walk converges to psi. Supposedly, I want to know more. So because I want to give a constraint on the possible behavior of all the paths that converge to psi. So here's one thing that you could ask for, which is, suppose I draw this geodesic. Okay, after n steps, okay, the drift is L. So roughly, I want to be at distance L times n from the origin, because L is the drift, okay? So I pick a point along the geodesic at distance L times n. Now the question is this a good prediction of where the walk is? And this depends, right? So it depends on the distance between the n step of the walk and the geodesic at time L times n. Okay? So we say G mu has the sublinear tracking property. If for almost any, so again, let's see what other things we can pick O in X. Okay, if for almost every sample path, there is a geodesic ray gamma. So what's a geodesic ray? It's an embedding of a half line into X There's an isometric embedding of a half line into X, that's geodesic ray, such that, well, the distance between the n step of the walk, the distance between the n step of the walk and gamma at step L times n divided by n goes to 0. So if that's the case, we say that the walk has sublinear tracking property. So this distance is small o of n. And so what it turns out that this type of condition is enough to pin down the Poisson boundary. In fact, yeah, there is one minor thing to say is that in most cases, if this is the case, then the limit, note, the limit as n gets to infinity of gamma Ln as to equal the limit as n goes to infinity of Wn for almost. This is space in the boundary. So this might slightly depend on the compactification, but of course, the other thing we want is that this geodesic ray that you have converges to the boundary point that you want. This is because what we want is we want to say that you have a boundary point, and from this boundary point, we condition on every path that converges to this point. And so the way to make sure that we can control the set of paths that condition to that is, okay, we take the geodesic that converges to that point.
Do you see uniqueness?
No, I don't think you need some. No. No. You need, eventually we will see that you need some sort of measurability, like that everything can be sort of equivariantly defined in a nice way, but no. No, the uniqueness would be very strong, but it's not. Yeah. Okay, so in fact, so here's the theorem, which is the Ray criterion. Okay, Ray criterion is slightly more general, but this is basically the way that it gets applied the vast majority of times. Okay, so again, under all these assumptions, so again, let the G mu we measure group. Acting by isometries, okay, even it doesn't have to be a subgroup, but there is, okay, that has to be G action, so a homomorphism into group of isometries of some space, geodesic metric space. And with the modification for equals x in boundary. So remember that modification means that the action extends to an action by homomorphisms. on the bound on X unions the boundary, and also that X is dense in the bodification. Okay, and okay, you let O in X and suppose the following. Okay, so the first thing you suppose that for almost every sample path, the limit exists. Exists on the boundary. And the second is that you have this linear tracking properties. Also, we need a exponential. Yeah, if we're looking at any action like this, we need an exponential growth condition. So let's say the following. So the action has exponentially bounded growth, meaning the following, that the number of G's in G such that the distance between O and GO is less than R. This has to be bounded by C e to the CR for every R. So for every ball in the space, the number of elements of the group that gives rise to that is somewhat bounded. So for instance, an action of a group on a Cayley graph, on its Cayley graph for a finitely generated group, that's always the case, but in general, maybe trickier.
Speaking ranking group is finitely generated. It is not always true.
No, because the action could be really bad. So, could be the trivial action of G on a point. Then the growth would be an orderless, right? So for most reasonable spaces, like groups acting on manifolds, this is usually the case. But
Action is free.
right, so if the action is free and the group is finitely generated, then if the action is properly discontinuous, then it's true. Yeah, exactly. But X could also be a much more complicated space. It could be a locally infinite graph, for instance. Then the set of points with distance 1 could be infinite. So there are like other annoying things going on. But let's say this is a classical case. You have a group acting on itself or on a manifold in a, like, for instance, mapping class group acting on Tegmark space is another example like that. So okay, and then the other one is, okay, so that the measure has finite first moment. So the measure has finite first moment. And the linear tracking property holds. Okay, then indeed, this is the Boston number. Okay, so So in fact, this theorem can be applied in any situation where the space in which G acts as some hyperbolicity. So what's the idea of the proof? So the idea of the proof is the following. It's pretty easy, actually. It's like that. So we need to check. We need to control the entropy of P psi. So this is, which is the limit as n goes to infinity of the entropy of this mu and psi divided by n. So we are given psi, which is the boundary point. And so we are looking at all the paths that converge to psi. However, we have one good thing for us, which is we know the sublinear tracking property. So out of all the paths that converge to this psi, can we guess where the n step is? That's the point. And so Wn is somewhere around here. And so gamma is here. This is gamma of Ln. And so what does the sublinear tracking property say? So the sublinear tracking tells that the distance between W and O and gamma Ln divided by n goes to 0. Okay. So in fact, so how big can this, so how many options do you have for Wn? That's the thing, right? So okay, so you fix epsilon, let's say, so the fix epsilon. And what do we have? We have that the probability under psi that WNO belongs to the ball around gamma Ln or radius epsilon n this is going to 1. Right? Why? Because, well, because the distance is less than epsilon times n. Right, so the distance here, so if you draw a ball around this point, well, almost surely you're gonna lie inside that. In fact, in probability, you're gonna converge. And so what is the entropy associated to this event, right? Well, you see that's the cardinality of, right? So the entropy, right, of psi, yeah, the entropy of mu and psi Well, you see, this event has probability that is going to 1. So this probability, let's call it an psi. Yeah, so we do the similar computation as we did before, right? It's like what? It's like minus the sum. So yeah, before I think we got something like this. So we got sum of G in A and psi, mu and G log mu and G minus G is in the complement. And so right, so then in the end, what can we estimate here, right? So basically in the end, we're gonna get something like log of the cardinality of A and psi plus a constant. And then, okay, then we get this integral here. Yeah, so this integral here, again, much like we did before, it's an integral of something of a small set. Yeah, so this is a small set. Okay, there is some estimate to be made here because the measure is not necessarily, if the measure is finitely supported, then it's completely exactly the same as we said before. Now the measure is not finitely supported as finite first moment. So maybe there is a little bit to discuss about this. But what matters is this term, right? So this term here, what is it? This is the log of the cardinality of the bulk around gamma ln of radius epsilon n. And so this one, so we know also that this action has exponentially bounded growth. So the number of elements in a ball of radius epsilon times n is E, yeah, is some R times epsilon to the n. Yeah, so right. So okay, so this plus some higher, this is a small term, but okay, let me finish this discussion here. So here recall, right, that the number of elements, yeah, in a group, so the number of G in G such that B, yeah, such that GO is in the ball around O of radius R. This one was less than C e to the CR, something like this. So if you take the log of that, so we take the log of that, well, this is less than basically C times R plus something small. So in any case, what I want to say is that if you have this term, this is less or equal than epsilon C, yeah, basically epsilon C n. Epsilon C n, and again, plus small order terms. So clearly this is less than, yeah, this divided by n, this goes to 0 for everything. So the limit soup as n goes to infinity, of h mu n psi divided by n is less or equal than epsilon c for every. That's again the and so of course so of course it has to be 0. So h. So the limit in the end then just infinity of this divided by n. Again, what is the main point? The main point is that since we know that the walk converges to psi, we have good control because we take this point gamma of Ln, and we know that the nth step of the walk has to be within, say, radius epsilon n for any epsilon. And so the number of possibilities here is basically sub exponential. And so if you take the log of that, you divide by n, it goes to 0. So that's why the entropy is the relative entropy is 0. And so in the end, n nu x nu is the positive. Okay, so that's the basic mechanism that shows how the geometry, knowing something about the geometry of the walk will tell you something about the identification of the Poisson boundary at infinity. And we'll see that there are variations of this criterion, and you can try to weaken certain assumptions here. For instance, you can weaken the moment condition. So this will be the most recent work we've done, which in fact we will show in the last lecture, that indeed you can weaken the moment condition to having no moment condition, but you still need a finite entropy condition because you want to estimate this entropy at infinity. Okay, so maybe for today, maybe it's enough. So I don't know. Are there any questions?
It looks like we generally use the log in part of the entropy. So if we find the entropy as something like anything times some linear times linear.
Well, I'm confused. So here we are using the log. I mean, we're using the convexity of the log first, like you need the Jensen's inequality type thing. And then we are using, well, I mean, the growth is exponential, so you have to take the log of it to make it into linear. So in that sense, we're using the log. I don't know exactly what you have in mind as. Yeah. So yeah, it is true that it's a somewhat soft estimate because we really go directly to estimating the cardinality, which is sort of easy way. And that's why, in fact, when you go to more sophisticated groups like the Lamplighter group, for instance, maybe it's harder to estimate this. Yeah, it's not that simple, but still, yeah. Or even when you don't have moment conditions, I mean, the issue is you cannot take the ball because you don't really know that the walk is constrained in the ball. So that's why there needs to be a more subtle thing. Okay, good. Other questions? Okay, if not, then I guess I'll see you on Thursday then. Yeah.